So let's start with the theoretical background. Unfortunately, our time is limited here, so we will try to give only an overview about the basic mathematical and mechanical background of our topics. First, we will have a look at the natural vibration analysis. Natural frequency or eigenfrequency is the frequency at which a system oscillates if there is no driving or damping force. The form with which the system oscillates is called the eigenmode. The natural frequencies and modes are important. They are key properties and describe the dynamic behavior of the system both in free vibration and under excitation. Input for modal response spectrum analysis, as we will see it later. We can evaluate the structure if there is any chance of resonance. We can use it for further analytical calculations and hand calculations, for example wind dynamic, vortex shedding analysis, pedestrian-induced vibration analysis, and so on. An elastic continuum has unlimited natural frequencies. For some of them, such as a single-span beam, we have the exact analytical solution. We see here the formula for the natural angular frequency and for the eigenmode as well. In case of complex systems, however, we have to use discretization. The basis for the discretization is a single degree of freedom system consisting of a point mass and a spring. This is the simplest system for which we can calculate the natural frequency. The dynamic behavior of such a single mass system is described by a second-order ordinary differential equation. We have the equilibrium of the inertia force and the spring force. We can rewrite the equation in the following form. The general solution of the differential equation looks like this. As we can see, the natural vibration is a harmonic vibration with the angular frequency described by omega. The natural frequency and period can be easily obtained from the angular frequency. If you have a more complex, multi-degree of freedom system, we have basically the same solution, but we have to work with matrices. So, we have a system of equations like this. The K matrix is the stiffness matrix, well known from simple static calculations. There are different options to compose the mass matrix of the system. The easiest way is to use lump masses in each node and construct a diagonal mass matrix. In this case, only masses in the translational directions are considered. This can be extended with the mass moment of inertia terms of each mass point. The most complex mass matrix is the consistent mass matrix. In this case, the masses are not lumped into nodes, but created using the shape functions of the considered elements. Note that there are non-diagonal elements, which means that the mass rotation in general is taken into account. On one hand, the diagonal matrix can be stored as a vector. It is easy to convert, so we can have a fast solution. On the other hand, the more complex the mass matrix is, the closer we are to the exact solution, of course. Generally, the contribution of non-diagonal members decreases with the element size, since the nodes are closer and closer to each other, and the center of gravity of the discretized system comes close to the global center of gravity. We go back to the original equation and try to find the solution using the following function. It gives us the following eigenvalue problem. For the non-trivial solution, the determinant of the expression should be 0. This is called the characteristic equation, and as a solution we can get the n eigenvalues, which are the square circular natural frequencies of the system, and n eigenforms, eigenvectors, which are the natural vibration modes. In case of complex systems, we have to use numerical methods to solve the eigenvalue problem. The most used methods are the Lanczos, the roots of characteristic polynomial, the subspace iteration, and incomplete conjugate gradient methods. In most cases, the eigenvectors are normalized to be able to use them in following calculations with different purposes. There are 4 common ways to normalize the mode shapes. The value of coordinate j of mode I is set to unity. The mode is scaled so that the maximum value equals unity. The mode is scaled to have unit length. The modal mass defined as a specified value. M equals 1 is often used, in which case the mode is normalized to the mass matrix. The natural modes satisfy important orthogonality properties. They are orthogonal both to the mass and stiffness matrix. This is really important, since this is a key ingredient for decoupling a large multi-degree of freedom system. So, the next topic we would like to present here is the Modal response spectrum method. This method is largely used in seismic analysis and design due to its relative simplicity. The method uses discretization of large systems, does model analysis and model decomposition using the orthogonal properties of the vibration modes, and determines equivalent seismic static loads for each vibration mode. It is a simplified approach, but it can be used in many cases according to various standards if some conditions are met. The application of the response spectrum method differs depending on whether all supports are moving in the same way or not. These are called single-point RSA and multi-point RSA. An example of multi-point response spectrum analysis is the analysis of a long bridge structure where the incoming seismic waves may be different at each support due to the large extent of the structure. For simplicity, we will present here only the single-point response spectrum analysis. We will assume again an Mdof system. Considering base excitation and introducing the relative displacement, the equation of motion can be rewritten like this. Dividing by the mass m, we obtain this final form. Here we have again the angular natural frequency, and we introduce also damping in the system with the velocity proportional c constant. In the last equation, we see the Cqc parameter, which is often used and describes the damping ratio of the structure. In the case of seismic design applications, the base excitation time history corresponds to the measured or artificial generated accelerogram. All we have to do is solve the differential equation and we obtain the displacements, velocities, accelerations, and therefore the inertial damping and spring forces of the system. The numerical solution may be obtained with step-by-step numerical integration methods, or methods based on the numerical evaluation of the duhamel integral. The first one can be used also for nonlinear problems. The duhamel integral is for linear systems. With the above mentioned methods, we can calculate the seismic response of an Mdof system for various natural periods, changing the stiffness and/or the mass of the system, considering different damping ratios. If we plot the maximum responses from a seismic record for a fixed damping as a function of the natural period, we obtain the so-called acceleration, velocity, and displacement spectrum of the seismic excitation. At 0-second period, the structure is infinitely stiff. The structure is moving together with the base, so their accelerations are identical, while the relative speed and displacement of the structure are zero. As we can see, the spectral acceleration depends strongly on the vibration period, so basically on the mass and stiffness of the system. Also, depending on the natural vibration period, the system may be sensitive to high accelerations, velocities, or displacements. All three parameters can be used to assess the damage caused by an earthquake, but usually we use the acceleration spectrum to define the inertial forces for force-based design. Since the spectrum already considers the dynamic properties of the system, such as natural period and damping, it can be directly applied for quasi-static calculations without the need of time-consuming dynamic analysis. Please note, however, the analysis can only be used for linear or equivalent linear systems. Now let's plot the same acceleration spectra, but with various damping ratios. As we can see, the damping is an important parameter. The response shows significant differences using different damping ratios. 5% of critical damping is often used in seismic codes, but this level is only justified if some structural elements dissipate the proper amount of energy. The estimation of system damping is therefore a really important issue in seismic design. The next question: how can we extend the analysis to Mdof systems? The key is the orthogonality of the mode shapes. We can decompose a large n degree of freedom system into n Mdof systems as follows. The system of dynamic equilibrium equation for an Mdof system is similar to an Mdof system, but in a matrix form. Here J is the influence coefficient vector. Now we perform a model decomposition by defining the displacements in terms of model coordinates and the corresponding mode shapes. In case of proportional damping, we get a system of n uncoupled equations corresponding to the n modes of vibration. Each mode is a separate Mdof system with their own model mass, damping, stiffness, damping ratio, natural frequency, and participation factor, which shows the importance of the observed mode. We can solve the equation using time history analysis and get the time series of the responses. This approach is, however, time-consuming, especially in case of large systems. From the Mdof system, we already know that the maximal displacement, speed, and acceleration can be defined in advance as a response spectrum. All we need is only the damping and the natural period of the vibration mode. After that, we have to transform back the model coordinates to get the real displacements, velocities, and accelerations. Once we have the nodal accelerations, the equivalent inertial forces can be calculated using Newton's law. For each mode, we can perform now a simple static calculation, avoiding the need of a dynamic analysis. If you use a step-by-step integration of the equation of motion, we would get a time series for each mode, and we could easily use superposition to sum up all the modes. In this case, we would get simultaneously occurring results, for example normal forces combined with bending moments as a function of time. If we use response spectrum analysis, we calculate the maximum value for each response and for each vibration mode, and therefore we lose the sequence and time series of the responses. For this reason, we need to use robust and statistically reliable model combination rules. The three most commonly used methods are the absolute sum, the square root of the sum of squares, and the complete quadratic combination. With the upsum method, we are summing up the absolute values of the peak responses of all considered modes. It assumes that all peak values occur at the same time, so it is an upper bound estimate and often very conservative. In case of the SRSS rule, the peak responses are squared, summed, then the square root is taken. This combination provides good results with well-separated modes. If two adjacent frequencies are close to each other, the Cqc rule should be used. The Cqc is a modified version of the SRSS rule. Note that each of the terms in the double summation may be positive or negative. As a result, maximum response estimated by the Cqc rule may be larger or smaller than the SRSS estimate. Several formulations exist for the correlation coefficient, but the one proposed by the Q is widely used. If the damping and frequency of two modes are identical, the correlation coefficient equals to 1. For small damping values, it is only a narrow range in the neighborhood of the frequency ratio, where we have significant values. Structures usually have a low damping ratio, about 5%. That is why standards suggest to use the Cqc rule if the ratio of two adjacent frequencies is within ±10%. The seismic excitation can be calculated in three directions. The combination of the different directions can be done with the upsum, the SRSS, or the 30% rule. The upsum method is too conservative. The SRSS can be used if the cross-correlation between the directions is very low. The 30% rule is proposed by many seismic codes and proved to provide reliable results. A structural system may have thousands of degrees of freedom. It is not realistic that we calculate all the existing vibration modes and combine them to get the results for the seismic analysis. But how many modes do we have to consider? Seismic design codes, such as Eurocode, use a parameter called effective model mass. In order to guarantee that a sufficient number of modes is used in the analysis, the sum of the effective model masses has to be larger than a certain percentage of the total mass. This is usually defined as 90%. As a summary, let's see the steps of the analysis. We will present some Eurocode relevant expressions and equations, but the basic idea is the same or similar in other seismic codes as well. The first step is to create the mechanical model of the structure. Then we use discretization. We compose the stiffness matrix and the mass matrix. The mass we consider should contain all permanent loads and the predefined part of the live loads as well. The amount or percentage is defined with the combination factor in Eurocode, and for example, we don't have to consider wind, snow or temperature loads in most cases. In step 5, we calculate the natural frequencies and forms of the system, and we make sure that we consider at least 90% mass of the whole structure. Then we define the standard spectrum for analysis. The standard acceleration response spectrum is usually an envelope of all expected earthquakes at the design site. In order to simplify and unify the various spectra, the envelope is defined conservatively to reduce the number of parameters to construct them. These parameters are usually the peak grand acceleration, the ground conditions, the magnitude and distance of the earthquake, and the damping. The presented spectra are elastic spectra for elastic design. If the structure has energy dissipation capacity, for example through plastic behavior, the spectrum can be reduced using the behavior factor. In this case, however, we have to make sure that the plastic behavior can develop and the energy dissipation occurs in the predefined members. This topic is too large itself, therefore it is out of scope to present it in detail. Using the dynamical properties, natural periods, damping, and the natural vibration forms of the system, we can define the equivalent seismic loads for each vibration mode. The defined load is theoretical in order to account for uncertainties in the center of gravity and also the spatial variation of the seismic action. Accidental torsional actions are added to the calculated forces. In step 8, we perform the static analysis. Then we combine the results for each vibration mode and each direction. After that, the seismic effects have to be combined with other load effects. According to Eurocode, we consider again the permanent loads and the part of the live loads acting simultaneously with the seismic load. The last step of the analysis is to check if the structure is sensitive to second-order effects. To assess the sensibility, we determine the interstory drift sensitivity coefficient for a story. Here P is the total gravity load above the considered story, D is the design interstory drift, V is the total seismic shear at the considered story, and H is the height of the story. We can categorize the sensitivity of the story and structure as follows. If theta is smaller than 0.1, the second-order effects are negligible. If it is greater than 0.1 but smaller than 0.2, we can consider second-order effects in a simplified way. If it is even greater but smaller than 0.3, we need to consider second-order effects during the analysis using nonlinear second-order solvers. If theta is greater than 0.3, the structure is too sensitive and needs to be redesigned. Based on this evaluation, we can update or recalculate the results and internal forces. The next step would be the design checks and verifications. These can be complex, code, material, and structure system specific. Therefore, due to time limits, it is out of scope in this webinar.